The cosmos has always been a theater of wonder, but sometimes it presents us with phenomena so unexpected that they force us to reconsider everything we thought we knew. The James Webb Space Telescope, humanity's most advanced eye on the universe, has recently turned its gaze toward an enigmatic visitor from beyond our solar system. The interstellar object known as 3I/Atlas. What it discovered there has left astronomers puzzled and fascinated in equal measure. Deep within this cosmic wanderer, Webb detected mysterious lights, glowing emissions and luminous patterns that don't fit the profile of any comet or asteroid we've encountered before. This isn't just another astronomical curiosity. It's a window into the alien chemistry, ancient journeys, and perhaps fundamentally different physics that govern objects born around distant stars. When 3I/Atlas was first spotted streaking through our solar system, astronomers immediately recognized it as special. Its trajectory was hyperbolic, meaning it came from interstellar space and would eventually leave our system behind, never to return. This made it only the third confirmed interstellar object ever observed, following the famous Oumuamua in 2017 and Comet 2I/Borisov in 2019. Each interstellar visitor offers a precious opportunity to study material formed in another star system, carrying clues about planetary formation processes that may differ radically from our own. But 3I/Atlas quickly distinguished itself from its predecessors. Even in early observations, it exhibited unusual brightness characteristics that didn't match standard cometary behavior. Most comets brighten predictably as they approach the sun, their ices sublimating and releasing gas and dust that reflect sunlight. 3I/Atlas, however, displayed an intensity and pattern that suggested something more complex was happening beneath its surface. The James Webb Space Telescope was brought to bear on this mysterious object in August 2025, using its near-infrared spectrograph to peer into the chemical composition and physical processes at work. What Webb revealed was startling. The telescope detected bright emissions and unusual light signatures in the infrared and near-infrared wavelengths emanating from within the object's coma, the cloud of gas and dust surrounding its nucleus. These weren't simply reflections of sunlight or standard thermal emissions from a warming surface. Instead, the data showed concentrated regions of luminosity, bright spots that appeared to be tied to active internal processes. The light patterns suggested localized jets, hotspots, or areas where material was being released with unusual energy. The distribution was not uniform, indicating that 3I/Atlas possesses internal structure and complexity far beyond a simple frozen rock drifting through space. What makes these mysterious lights particularly intriguing is their chemical signature. Webb's spectroscopic analysis revealed that 3I/Atlas has an extraordinarily high ratio of carbon dioxide to water vapor, among the highest ever recorded for any comet. In typical solar system comets, water ice is the dominant volatile, and as these objects approach the sun, they release copious amounts of water vapor that creates their characteristic tails and comas. But 3I/Atlas defies this pattern. Its coma is dominated by carbon dioxide emissions, with water vapor significantly suppressed. This unusual composition suggests that the object either formed under radically different conditions than comets in our solar system, or that it has undergone substantial alteration during its long journey through interstellar space. The lights we see appear to be directly connected to this carbon dioxide outgassing, as the bright emissions correspond spatially and spectrally to regions of intense CO2 release. The implications of this discovery extend far beyond mere astronomical novelty. The composition and behavior of 3I/Atlas offer insights into planetary system formation in other parts of the galaxy. The high carbon dioxide content suggests the object likely formed beyond the CO2 ice line in its parent protoplanetary disk, a region where temperatures were cold enough for carbon dioxide to freeze into solid ice. This is farther out than the water ice line, indicating that 3I/Atlas may have originated in the outer reaches of another star system, where conditions differed markedly from the region where Earth and other inner planets formed. If comets in other systems are more carbon dioxide-rich than water-rich, this could have profound implications for how volatiles are delivered to planets in those systems and consequently for the potential habitability of worlds orbiting distant stars. Beyond carbon dioxide, Webb detected other intriguing substances in 3I/Atlas. Spectral lines indicated the presence of carbon monoxide, another volatile that sublimates at great distances from the Sun, as well as unexpected emissions of nickel vapor and cyanide compounds. These substances are occasionally found in solar system comets, but their proportions and characteristics in 3I/Atlas are unusual. The presence of metal vapor, in particular, suggests that the object's nucleus may contain materials that are being heated and released through processes we don't fully understand. Some scientists have proposed that cosmic ray bombardment during the object's long interstellar journey may have chemically altered its surface layers, transforming carbon monoxide into carbon dioxide and creating an organic-rich crust tens of meters deep. If this is the case, the mysterious lights we observe may be revealing both the pristine interior and the processed outer layers simultaneously. The spatial pattern of these lights provides further clues about the internal structure of 3I/Atlas. Rather than a uniform glow, the emissions appear concentrated in specific areas, particularly on the sunward side where solar heating is most intense. This asymmetric pattern suggests that the object's surface is not homogeneous. There may be fractures, faults, or thin spots in an insulating crust that allow volatiles from deeper within to escape preferentially in certain directions. The lights effectively map out the architecture of the nucleus, highlighting where heat penetrates most effectively and where subsurface volatile reservoirs are being tapped. This kind of structural information is extraordinarily difficult to obtain for objects so distant and small, yet the luminous emissions act as natural beacons, revealing hidden features that would otherwise remain invisible. One of the most remarkable aspects of the lights in 3I/Atlas is what they tell us about the durability of interstellar objects. The fact that this visitor still retains enough volatile material to produce significant outgassing and bright emissions means that its reserves were not stripped away during potentially millions or billions of years of travel through the harsh interstellar environment. Cosmic rays, which can penetrate and chemically alter surface materials, apparently did not completely deplete the object's ice content. This suggests that interstellar space may be less destructive to small icy bodies than some models predicted, or that 3I/Atlas has protective features, perhaps a thick insulating mantle or a larger size than estimated, that preserved its volatiles during the long journey. The endurance implied by these lights indicates that many more active interstellar objects may populate the galaxy, dormant until they approach a star and awaken to produce the spectacular displays we're now witnessing. The detection of these mysterious lights has also opened up new methodologies for studying interstellar visitors. Before the James Webb Space Telescope, our ability to analyze such objects in detail was limited. Ground-based telescopes could track their motion and measure basic properties, but lacked the sensitivity to probe internal processes with precision. Webb's infrared capabilities changed the game entirely. By detecting faint thermal emissions and mapping the distribution of gases and dust with high resolution, Webb allows astronomers to conduct detailed diagnostics of objects that are millions of kilometers away and moving rapidly through the solar system. The lights in 3I/Atlas demonstrate that interstellar objects are not simply passive targets for observation but active laboratories where we can study exotic chemistry and physics in real time. Future observations of similar visitors will undoubtedly employ these same techniques, looking for luminous signatures, emission patterns, and structural features that reveal their origins and histories. The mysterious lights also raise intriguing questions about the diversity of cometary objects throughout the galaxy. Our understanding of comets has been shaped almost entirely by the study of objects native to our solar system, all of which formed from the same primordial cloud of gas and dust that gave birth to the Sun and planets. We've naturally assumed that comets everywhere would be broadly similar. Icy bodies with water as the primary volatile, embedded with dust and organic compounds. But 3I/Atlas challenges this assumption. Its carbon dioxide dominance and unusual composition suggest that comets formed in other stellar environments may follow different rules, reflecting the unique conditions, temperatures, and chemical inventories of their parent systems. The lights we see are not just interesting in themselves. They represent evidence of a wider diversity in the cosmos than we had anticipated. Every interstellar visitor that passes through our system brings with it the potential to expand our understanding of planetary system formation and evolution across the galaxy. There is also a temporal dimension to consider. The lights in 3I/Atlas are not static. They change as the object moves closer to or farther from the Sun. As it approached perihelion, the point of closest approach to our star, the intensity of outgassing and the brightness of emissions were expected to increase, revealing how the object responds to varying levels of solar heating. By tracking these changes over time, astronomers can learn about the thermal properties of the nucleus, the depth and accessibility of volatile reservoirs, and the efficiency of heat transfer through the object's structure. Each phase of the object's journey through the inner solar system acts like a natural experiment, probing different layers and processes. The evolving lights thus provide a dynamic record, a movie rather than a snapshot, of how an interstellar comet behaves when it encounters a new stellar environment. The question of age adds another layer of fascination. Some estimates suggest that 3I/Atlas could be billions of years old, potentially predating our solar system itself. If true, the lights we observe are emissions from an ancient relic, a fragment of an early epoch in galactic history when star formation and planetary system creation were proceeding under different conditions than today. The chemical signatures preserved within this object, revealed through its luminous outgassing, would then constitute a time capsule, offering a glimpse into the chemistry and physics of the early galaxy. This perspective transforms 3I/Atlas from a mere curiosity into a scientific treasure of immense value. Every photon of light that reaches our telescopes from this object carries information that spans cosmic timescales, bridging the ancient past and the present moment. Of course, the mysterious nature of the lights has not escaped the attention of those interested in more speculative possibilities. While the scientific consensus firmly holds that 3I/Atlas is a natural object, an interstellar comet with unusual but explicable properties, the very fact that some aspects of its behavior don't perfectly match standard models has led to broader questions. Could there be physical or chemical processes at work that we haven't yet discovered? Might internal heat sources, such as radioisotope decay or structural changes, contribute to the emissions? These are legitimate scientific questions that push the boundaries of our knowledge. More speculatively, a few researchers have pondered whether any aspect of the object's behavior could hint at artificial origins or technological components, though it must be stressed that no credible evidence supports such ideas. The value of keeping an open mind lies not in embracing unfounded speculation, but in recognizing that the universe often surprises us with phenomena that challenge existing theories and demand new explanations. From a practical standpoint, the lights in 3I/Atlas have implications for future space missions. If humanity ever mounts an expedition to intercept and study an interstellar object up close, the luminous regions detected by Webb would serve as prime targets for investigation. Knowing where the active areas are, where volatiles are escaping, where internal heat is concentrated, would guide mission planners in deciding where to aim instruments, collect samples, or even land probes. The lights effectively provide a roadmap of dynamic activity on the object's surface and in its coma. Moreover, the spectroscopic data gathered by Webb inform the design of instrumentation for such missions, highlighting the need for sensitive infrared detectors, spectrometers capable of analyzing complex volatile mixtures, and imaging systems that can map thermal and compositional variations across the nucleus. The study of 3I/Atlas and its mysterious lights also underscores the importance of rapid response capabilities in astronomy. Interstellar objects pass through the inner solar system quickly, offering only a brief window for detailed observation before they recede into the darkness and become too faint to study effectively. The ability to quickly mobilize advanced telescopes like Webb, coordinate observations across multiple platforms, and analyze data in near real time is crucial for maximizing the scientific return from these fleeting visitors. The lights detected in 3I/Atlas were captured because astronomers acted swiftly, recognizing the object's significance and prioritizing observing time on premier facilities. This experience will inform strategies for responding to future interstellar arrivals, ensuring that we don't miss opportunities to learn from these cosmic messengers. As we reflect on the discovery of mysterious lights inside 3I/Atlas, it's clear that this object has already transformed our understanding of interstellar visitors. It has shown us that comets from other star systems can be profoundly different from those we know, both in composition and behavior. It has demonstrated that interstellar objects can remain active and dynamic even after journeys spanning unimaginable distances and timescales. And it has proven that modern telescopes, particularly the James Webb Space Telescope, possess the capabilities needed to unlock the secrets of these enigmatic travelers. The lights within 3I/Atlas are more than just an observational curiosity. They are a revelation, illuminating processes and conditions in distant reaches of the galaxy that we would otherwise never glimpse. Looking ahead, the legacy of 3I/Atlas will likely be measured not only by what we've learned from this particular object, but by how it has prepared us for future discoveries. Every interstellar visitor that enters our solar system is unique, carrying its own story written in the language of chemistry, physics, and light. The techniques developed and refined in studying 3I/Atlas, infrared spectroscopy, thermal mapping, compositional analysis, will become standard tools for examining the next such object, and the next. With each visitor, our understanding will deepen, and the mysterious lights that once baffled us will become familiar signposts, guiding us through the complex landscape of interstellar material science. The cosmos is vast, and we are only beginning to read the messages it sends our way in the form of these wandering ambassadors from distant stars.